On these executed discretizations, the deep spectrum falls into a numerical killing zone, failing simultaneously on mathematical precision and physical observability. All of the data we are examining today is strictly bounded. We are looking exclusively at executed finite grids locked at an epsilon value of 0.70. The matrix dimensions for this analysis are highly specific, scanning resolutions of exactly 8,192 and 16,384 cells. At these resolutions, we are targeting the WBA and Lorentzian kernels applied directly to the twisted birdmap boundary grid. It is standard mathematical folklore that if you have a geometrically clean, narrow right eigenvector, you can trust its associated eigenvalue to be stable. Our previous research in paper 56 already challenged this assumption by exposing massive conditioning proxies, labeled kappa J, hiding within these exact modes. That underlying leakness in the conditioning proxy is the precise mechanism that causes these eigenvalues to systematically fail when calculated on standard hardware. This brings us to the first axis of failure, precision collapse. We calculate the predicted float 64 drift, delta J, by multiplying the conditioning proxy, kappa J, by the machine epsilon. The machine epsilon is a hard, fixed constant. It represents the absolute arithmetic limitation of IEEE Sin 54 double precision. When a deep tier generates a conditioning proxy on the order of 10 to the 18th power, it acts as a catastrophic multiplier against that otherwise tiny machine epsilon. While Tier 1 remains perfectly safe from this effect, the deep tiers are completely consumed. The resulting arithmetic drift entirely outscales the actual modulus of the eigenvalue itself. Scanning these grids, 32 of 40 tiers failed the precision test. A single machine epsilon perturbation destroys the eigenvalue entirely. At 16,384 resolution, the failure is extreme. Drift ratios hit ranges of 10 to the third up to 10 to the 7th power. When arithmetic drift generated by a calculation is larger than the computed value, that value is informationally void. It is arbitrary noise masquerading as data. This precision collapse is driven by a deep spatial blurring. As we look at tiers 3 through 10 in the killing zone on both axes, the left eigenvectors spread across thousands of cells. This massive spatial spread creates our second axis of failure, observable disintegration. In this system, the left eigenvector serves a very distinct role. It dictates the physically accessible measurement, or the observable, for the system's corresponding modes. If an observable spreads perfectly flat across the entire grid, it becomes impossible to isolate that specific mode using any local measurement. To understand why the mathematics break down, we must look at the severe spatial conflict between the highly localized right eigenvector and its corresponding left observable. Look at this structural contrast. On the right eigenvector side, the geometry remains sharply localized, typically occupying a 90% support width of just 2 to 3 discrete cells. But the scan results for the left eigenvector reveal that the support for deep tiers smears out across 558 to over 3,600 cells. We formalize this asymmetry using the support ratio metric, sigma j, which divides the left support width by the right support width. The geometry scan is definitive. Across all 20 scanned deep tiers for both the WBA and Lorentzian kernels, the support ratio is uniformly greater than 100. This geometric disparity directly attacks the biorthogonal overlap. The extreme spatial mismatch between a 3-cell spike and a 3,000-cell smear forces their dot product rapidly towards zero. Driving the overlap towards zero is exactly what causes the massive conditioning proxies we identified in Act 1. The geometry causes the arithmetic to fail. Because of this severe spatial delocalization, no localized physical measurement can extract these deep modes from the background state on these executed grids. Scans reveal a 3-layer taxonomy. Tier 1 is the safe zone, the global stationary distribution. Tier 2 survives precision, but is physically dead with support ratios over 1,500. Tiers 3 through 10 form the killing zone, totally collapsing under fatal precision drift and observable disintegration. A visually clean right eigenvector is a mathematical illusion if the mode itself sits within this deep killing zone. It is critical to enforce our guardrails here. This entire three-layer taxonomy is strictly a property of the finite grid computation at an epsilon of 0.70. The digital disintegration of these matrices does not imply a failure in the underlying continuum dynamics or the asymptotic theory. The continuous bounded variations spectral gap that we verified in paper 37 remains perfectly intact. Tier 1 survives. Tier 2 is already unmeasurable. Tiers 3 through 10 are dead on both axes, on these executed grids. The continuous theory survives. It is the digital microscope that fails.